let's take a look at some of these.
No, I don't. I hate when people say that. It's not true. Just like we say 2 parts for a first name.
Now,
Good afternoon. Mr. Mattson is ready to begin the makeup session in the guidance office for the following juniors: Dennis Harms and Emily Kosky. Once again, Dennis Harms and Emily Kosky, please report to the guidance office for your makeup NISA testing. Kenwal Nas, please report to the main office. Kenwal Nas, please report to the main office. Thank you.
I got up and then took a step back. I'm more nice little like 21 minutes. Like the whole desk is grassy down. I know that.
That's great.
I was told her.
You were there. I think you were on the other side of the screen. Yeah, that's right.
It's funny.
And then I saw them and I was like, right before he went down.
So you could have warned me.
Yeah. As of right now.
Did you find yours, David?
It would have been quite as funny.
All right, let's run through the answers real quick. See if you've got some you have questions on. Now, I think it might be worth. We're going to move on today to the next section in the book. Still using integrals, but we're moving away from the volume thing, so that we really have nothing new to add to volume. That'll be a big part of the quiz next week, area and volume. These next 2 new things we learn will be a part of it. They'll be a smaller part of it. So we want to make sure that we really feel comfortable with these volumes. And I know some of you finished them up yesterday in class, but so maybe you feel pretty good about them. But I think it might be worth going through a few if we could. So number 4, what did you have for that one? 8 pi thirds. What was the next one? 7, 9, 9. 16 pi thirds, 12. Now that was when you had to divide into 2 parts, right? Okay. Do we look at that at all? Okay. Now, I would say, let me make a comment or two about 12 though. It says y equals 1 over x. And that's this function here. Then you have the line x equals 1 and the line x equals 2. So this would be the point 2, 1/2, and this would be the point 1, 1. Now normally, if on the quiz you were asked to revolve this region around the x-axis, what would you do? Slices? Disk method? Which way would the strip go? Vertical. So this would be just a very, very much a routine, right? Rotate the strip like so. And so the integral would be what? I mean, this would just be some good review here. Integral would go 1 to 2. Pi r squared, right? Because it's a disk, it's a circle. So pi r squared, and the r would be top y value minus bottom. So 1 over x minus 0. So 1 over x squared. That would be it, right? And you said that was what? Pi halves? Okay, that would be pi halves. But if we're going to do a horizontal strip, if we're going to do a shell method, we're going to have, right, the shell method, you've got wrapping, right? So the strip is parallel to the axis of revolution. So this would have to be split right there, because you'd have a horizontal strip would go there, and this horizontal strip would go there. correct? All right, so if I solve this for x, I get x equals 1 over y. So just very quickly then, we said for p, we just label the strip, right? Because this strip has some y location at 0, at 0.1, 0.2, 0.3, 0.4, 0.5, somewhere in there. And this one has a y location of 0.6, 0.7, 0.8, something like that. So let's do the top section. What's p on that one? What would be p on this top section? Y minus 0, right? It's the distance from the strip to the center, and this is the center. So y minus 0. And what would be the h? H is always the length of the strip. So that'd be this x coordinate, 1 over y, minus this one, which is, whoops, not 0, 1, right? 1 over y minus 1. So we would have 2 pi p, and then that goes from what to what? The top one. The strips go from 1/2 to 1. Okay, and then you do the bottom section much the same way. Okay, p would still be y because it's the distance from the strip to here, so it's still y minus 0. So if the strip is at 0.4, it'd be 0.4 minus 0. That's how far away from the center it'd be. So the other one would just be 2 pi. It would go from 0 to 1/2, and p would be y, and what's the strip? Strip is just 2 minus 1, so that would be 1. So there it would be. Okay, so there's the shell method. Here's what it would be if we would have done it these. Okay, 17. What'd you get on 17? 192 pi over 5. Now, I want to do this. I think you were supposed to do this as shell method, right? So if we got y equals square root of x, this line here was at 4, and you were supposed to revolve it. Did you revolve it around y equals or x equals 6? Okay. Now, you guys did the shell method yesterday. What type of strip would you have for shell method? Okay, because here's the axis of revolution, so the shell method wraps around it like this. Okay, so we would do vertical, so vertical strips are usually good. We label that vertical strip as x. So therefore p would equal what? 6 minus x. How far is the strip from the center? Here's the center. It's from here to here. If this strip was sitting here at 2, how far is it from the center? 4, 6 minus 2. If the strip is sitting here at 3, it's 3 away, 6 minus 3. So wherever the strip is setting, whatever x position that strip is at, that's how far it is from the center. That's what p is. Okay, h is y value minus bottom y value. So the integral is 2 pi 6 minus x times square root of x dx. From strips fill the space from 0 to 4. That's how you take care of the empty space. It only goes from 0 to 4. For review, how, and some people on the quiz will do this. They'll do it both ways just to check. How would you do this slicing? If you were going to do slicing method, what kind of scenario, what kind of slices would you have? Washers, donuts, right? Washers or donuts because you've got this empty space. So you'd have an outer radius, there, and an inner radius there, right? And so we would have big R would equal what? It'd be, I'm sorry, maybe I heard it, but I heard some wrong. 6 minus, what's this x coordinate? This x coordinate is y squared, right? X equals y squared. So 6 minus y squared would be big R. Little r would be 6 minus 4, which is 2. So the integral would be from, strips would go from 0 to 2, pi on the outside, big R squared minus little r squared. That would be doing it with a slice. They'd be washer slices, horizontal strips. So any of these revolving solids, we have a choice. We can do them shell, or we can do them disc or washer. Okay? It just depends on which way the strip is and which way you'd rather do it. One like that was just as easy. I don't think you could say it was harder one way or the other. I think those are probably equally easy. They wanted you to do shell method, I think, on 17, so that's probably the one you chose. All right. 21A. Now we had this region here on 21. We had y equals x cubed. That's the point 28. Here was your region, and I think on part A, what do you get for an answer? 128 pi over 7. Okay, part B, 60 pi over 5. Now, on this one, you were supposed to revolve around the x-axis right here. Or the y-axis, x equals 0. It's revolving around the y-axis. So what choice did you make? Which method did you do on this one? Shell. Shell would give you a vertical strip. So shell's pretty good. Shell would be a good choice. Okay? What is P? X minus 0, because there's your center. H is x cubed minus 0. So we got y equals x cubed. Okay, there it is. So you'd have 2 pi, 0 to 2 for the strip, x times x cubed dx. What if you wanted to do the other choice? What if you wanted to do slices? Would it be a washer? Little r, big R. Radius always goes to the center. So big R would be this x, 2 minus that x, 0. Little r would be this x, what's that x? Cube root of y, or y to the 1/3. So it'd be y to the 1/3 minus 0. So that'd be big R, that'd be little r. So we'd have 0 to what? 0 to 8 would be your strips on that one. Pi on the outside, big R squared minus little r squared. Either one of those would be fine, and they're both pretty easy to set up. Okay, that was 64 pi over 5. What about C? 96 pi over 5. And D? 320 pi over 7. 320 pi over 7. Want to see any one of those? Okay, they just move the axis on you. And so that's pretty good review of shell, of the disc or the washer. And then, of course, what we had yesterday, the base of the solid and then slices coming up off of there. Of course, that's a slicing. Those are the slicing ones. And that's it. I mean, those are your volume problems. All right. Well, get your books out. You're going to need your books today. Today we're going to learn how to do work. for some of you, if you've been in physics, you know all about work. Right? What is work? Force times distance. What are the units of work? Newtons times meters. If you're in science class, for some reason the science people have gotten on board with the metric system a lot faster than the math people. The math textbooks always seem to use English units. But if you're in science class, you're probably going to use Newton meters. That's how we say it, Newton meters, Newtons times meters. Now I think that has another name, joules. Is joules the same as Newton meters, I think? I think that's right. But you just usually say Newton meters. In English units, it's foot-pounds. Now, it's kind of backwards. The force is the pounds and the distance is the feet. But we usually say foot-pounds. Newtons is the force there. Pounds is the force. Typically weight. Okay, the problems we do, we'll think of the force as the weight. Okay, most of the problems we deal with are working against gravity. Okay, so weight is the component of force. So most of the problems we do will be in foot-pounds. Foot-pounds. Feet times pounds. Now, we're going to use the integral to do this. Why are we going to use the integral to do this? Well, if I took this textbook, what work is if you lift, a lot of times it's lift, or any force, if you push something or whatever, but if I lift this book through a distance, I've done work. Okay, the weight of the book times the distance. So if this book weighs 8 pounds and I move it 2 feet, I've done 16 foot-pounds of work. 16 foot-pounds of work. Now if I just stand here and hold this book over my head, I'm not doing any work because there's no distance. I'm not moving it. Okay, so there's no work involved to just hold something. Okay, it's got to move through a distance. Okay, now in physics, high school physics, you would deal with constant forces. Okay, so the weight of the book would not change as I move it. Now technically, the book weighs more here than it does up here. Why? Because I'm farther from the center of the earth up here. So gravity has less of an effect here than it now. That's pretty negligible, so it's probably okay to ignore it. Okay, much more so than when we throw something in the air and say we're going to ignore wind resistance, right? Especially if we throw a piece of paper in the air, you know, and you say you're going to ignore wind resistance, that's kind of silly. But we could probably ignore that change in weight, right? But you would weigh less on Mount Everest than you would weigh here in Carmel, right? Because it's farther from the center of the earth. Again, not much difference. Okay? Now, but in calculus, what calculus allows us to do, and we've talked about this before with physics versus calculus, in position, velocity, acceleration kinds of things, in physics, all those formulas deal with constant acceleration. In calculus, we can deal with variable acceleration. Well, in calculus, we can calculate work with a variable force. It doesn't have to be a constant force. So we're going to do 3 kinds of problems. We're going to do stretching or compressing a spring. Now we're like, think of a slinky or something, you know, that kind of thing. Now, but we're going to go in one direction. So we'll pretend like we've got a spring attached to the wall, and we're going to pull it to stretch it, or we might compress it, okay, from its natural length. Okay, and how much work do we do? What force is applied through that distance? Because it varies. Because as you pull that spring farther and farther, what happens? It gets harder and harder to pull. It takes more force, more pounds, more newtons of force to pull it the farther out you get. So the force varies. So guess how the integral will be involved? Adding up bits of work. In other words, what we'll say is, well, if I took this spring and I stretched it, a foot, yeah, at the beginning of that foot, it would take a certain amount of force. At the end of that foot, it would take more force. But if I only stretched it an inch, the amount of force at the beginning of that inch and at the end of that inch would not change that much. If we make that unit, if that distance small enough, right, you know where we're going with this, right? If we make that amount of distance small enough, we could say it's pretty much a constant force. So we could say, okay, move this spring a little bit. How much work did you do? Move it a little more, how much work did you do? Move it a little more, how much work did you do? Move it a little more, how much work did you do? And use the integral of what?
Add them all up.
You guys are awesome. Add them all up. Use the integral to add them all up. So that's what we'll do. Okay, so it's a variable force, so we'll just take little tiny bits of it to where it's almost constant, and then use the integral. Okay, second example we're going to use is a bucket and a rope. If I lift, say you got a well with a bucket, rope attached to it, and I'm going to pull up that bucket. Okay? Now in physics you would do this problem, you'd say, okay, if it's a 50-pound bucket and you got a 70-foot rope and you lift it up, how much work did you do? 50-pound bucket, 70 feet of rope, 3,500 foot-pounds. But in physics, you would be ignoring the rope. The rope is a variable force because when I first start to pull the bucket, I'm pulling up the 50-pound bucket and 70 feet of rope. That has a certain amount of weight. But once the rope is halfway up, now I'm lifting the 50-pound bucket and only 35 feet of rope. And it's farther from the center of the earth, so it weighs less. And so we will actually ignore that one. We will continue to ignore that one. Okay? I think they maybe do an example in your book, to be honest with you, about how far you get for example 4. It's they do an integral from like 21 million to 21 million and 3 or something. You know, and they talk about the change in gravity. And I mean, it's just a tiny amount, so you could probably ignore it. But so that's what we're going to do with the bucket. Again, the same principle is going to apply. So as you pull it up, you've got less and less rope. You're lifting, so it's actually getting lighter. Okay, but the idea is we'll say, well, how much work do we do to lift it a little, and then lift it a little more, and then lift a little more, and then lift a little more, and then the integral will add up all that. Okay. The last example we're going to do is pumping liquid out of a tank. Okay. For example, you go to the gas station, fill up your car. Right? Buried under the ground is a big tank where the gasoline is stored. And there's a motor that pumps the gas up from the tank, up into the nozzle and out. Okay? How much work, how much horsepower motor does it take? How much work does it take to move that distance? Okay? Now that one we're going to do a little differently. Then talk about, you know, how much work do we do here, how much work do we do here, how much work do we do here. We're going to instead talk about a slab of water, like a cylindrical slate shaped, very skinny slab of gas or water, whatever it is. How much work does it take to lift it up? And then how much work for the slab under it, and the slab under it, and we'll add up all the slabs, okay? But again, it's that same principle. Okay, so to show you this, I may have to kind of flip back and forth here, because I'm trying to record this, but I've got a little stolen PowerPoint, purloined, pirated PowerPoint is what I've got here. Isn't purloined, doesn't that mean steal? Sure. Stolen? Purloined?
Yes.
You guys are supposed to be better. You guys should have a better vocabulary than me. Come on. It's Thursday. It's Thursday. Purloined. Okay, pirated PowerPoint. From Mr. Greg Kelly. All right. Same guy. All right. So, first we'll do the spring. Okay? So on the spring problem, how am I going to do this? I won't. We're just... Okay, you're going to want to write this down. You're going to want to write this down. Because your homework, we're going to go through a spring problem, we're going to go through a bucket problem, and we're going to go through a pumping liquid problem. And your homework is going to be those same kind of problems. Okay, so I think you're going to want to have these, probably these written down. So, first of all, for a spring. Okay, now we've got something called Hooke's Law. Force is proportional to the distance that it's stretched. The force, and that's what we've said, is as you pull the string, spring. As you pull the spring, it gets harder and harder to pull. So force is proportional to the distance, x. Okay, so the farther you pull it, or the more you compress it, the more force is going to be needed. Okay, K is called the spring constant. So for a particular spring, K will have a value. So here's what these problems will usually look like. So you don't have to write this whole thing down, but let's say you had a spring, and usually it'll say something like spring has a natural length, okay, of 1, or it might not tell you what it is. It'll just say we're going to stretch it this far from its natural length. But if I've got a spring attached to the wall here, this particular spring sticks out 1 meter. 1 meter, big spring. Okay? And that's its natural length, that rest. They tell us that it takes 24 newtons to stretch it out to 1.8. Okay? Now, in that Hooke's law, what is going to be F? 24 newtons is the force. Or pounds. On most of our problems, it would be pounds. 24 pounds of force. And what's going to be the X? Careful now. 0.8. X will be 0.8 because we stretched it 0.8. We stretched it from 1 to 1.8. So you really have to read the problem carefully. If the problem says you stretched it a distance of 1.8, then you would put in 1.8. But here it says we went from 1 to 1.8, so we went 0.8. So you go ahead and you use Hooke's law to find K for this particular spring. Okay, so just do that real quick. Put that in there. So every spring problem will start out finding the force equation. The force equation. Because the force is changing. So it has an equation, right? It's not a constant force. It's a changing force because the farther we pull it, the more it'll be. Okay, and you get 30, right? Yeah, go ahead and get your calculators out because we'll need them here anyway. So we get 30 for K. So that tells us that for for this particular problem, that's not mine though, is it? No. So for this particular spring, the force equation is 30x. Okay? All right. So then the question is, and normally this would have been asked, earlier in the original problem. But it says how much work is needed to stretch the spring 3 meters beyond its natural length. Okay? Now, they could have asked the same question and said how much would be needed to stretch the spring out to a length of 4 meters? Because that's really what we're doing, right? It starts at 1, we stretch it out to 4, we've really stretched it 3. But they said how much to stretch it 3 beyond its natural length. Now, some people think you just put a 3 in here. Well, no, because that just gives you 90 pounds. What's that telling? What's that? If you just plug the 3 in there, which don't do it because that's not right. But if you plug the 3 in there and get 90, what does that mean?
3 times 30 is 9.
Well, right, but what's that mean? That's 90 pounds. What's that mean? 90 pounds for that spring. What's that mean?
How much you have to pull at that?
At that, yeah, once you're out 3, that's how much force you're using at that point. Like, that's all that's telling you. It's not telling you how much work is needed. We got to do force times distance. Okay, now some people say, well, you take 90 times 3. No, that's not right either because it didn't take 90 pounds of force that whole time. It only took 90 pounds of force once you got out there. How many pounds of force did it take at the beginning? Well, none at the beginning, right? 0 before you started pulling, right? And then it gradually got more until 90. Okay, so it's a varying force. All right, so what we do is we set up an integral. Okay, our integral is going to be this. Now, what I'm really going to emphasize to you today is think about your units. Remember, the integral is an adder, and we want it to be adding up work. So we want it to be adding up foot-pounds or Newton meters. Well, what is your units on the force equation? Pounds or newtons. And what's the dx? Meters or feet. That's the distance. Remember we said we're going to pull the spring a little bit, and then a little bit, and then a little bit? Well, that's the dx. That little bit is the dx. So we got a force times a little bit of distance. That's what we got here. Force times distance. So we got foot-pounds. We got foot-pounds here. And so the integral then will add that up. Now, what will the integral be? What will we put for f? 30x. And what will the integral go from what to what? It's gonna be 0 to 3 or it's gonna be 1 to 4, which one do you think?
0 to 3.
It is 0 to 3. Because it's how much we're stretching it. Where are we doing the work? We're not doing any work, okay, from 0 to 1, right? It's the work is done from starting at 0 stretch to a 3 stretch. So it's gotta be from 0 to 3. If you put 1 to 4, you'll get a different answer. What would the integral 1 to 4 be? That would really be from 2 to 5, right? That would be from a stretch of 1 out to a stretch of 4, right? And that's not what we're doing. We're doing it from no stretch out to a stretch of 3. So the integral's from 0 to 3, 30x, and we don't get 270, we don't get 270, we get 135, right? 135 newton meters. Now, that's exactly half. Well, yeah, because it's a linear. That force changes in a linear way. It goes out from 0 force at the beginning to 90 pounds at the end, and it does it in a linear fashion. So that shit's probably almost like a trapezoid. You know, a trapezoid is the average between the left and the right. I'm not really surprised that it was half of if we'd have done the other thing we were talking about. So 135 newton meters or 135 foot-pounds you should get. Okay, over a very short distance, even a non-constant force doesn't change much, so we get that. So hopefully that makes sense. Kind of cool, all these different kind of applications we can have just from this one concept, this one idea. So we use the integral to add up all these small bits of work. All right, here we go with the bucket example. Okay? Now we're starting right off with the hardest one of all, okay? We've got a bucket full of water, the bucket's leaking, and we have to consider the weight of the rope. Now a lot of times we do a problem like this and we don't have a leaky bucket, okay? So let's pretend for a minute actually that the bucket isn't leaking, okay? Now they tell us that the bucket has 2 gallons of water, which is 16 pounds. Now sometimes they don't just tell you that, they'll tell you the liquid and they'll give you the density. What's the formula in physics for mass and density and volume? So mass is equal to density times volume, isn't it right? Density would be like pounds per cubic foot. Like in this case, we're talking about feet. So density would be pounds per cubic feet, and you take that times volume, which is cubic feet, and the cubic feet cancel, and you get pounds. So we want the weight of the, so sometimes they would have given you this as they would have said, okay, you've got so many cubic feet of water, or maybe so many gallons, and then the density of water is this many pounds per gallon. Okay, and you'd have to multiply those two to get the pounds. But again, you always got to think about what your units are. We want our integral to add up foot-pounds. We want our integral to add up foot-pounds. Okay, now, they do this by 3 separate integrals. They do one for the bucket, one for the water, one for the rope. Typically, when I write these, I just write it as one integral. Bucket plus water plus rope. It's totally up to you. We'll go through the PowerPoint here as doing them separately. Okay, so typically what we do, so it wouldn't be bad to draw a little picture of this. It wouldn't be bad in your notes probably to draw yourself a little picture. I think that can be helpful. I mean, it doesn't have to be fancy, but. So 0 is with the bucket down at the bottom of the well. Okay, 20 up here. All right, they're going to start with the bucket. That's the easiest of all. You wouldn't even need, since a bucket's not going to change, again, we're going to ignore gravity. So you could just, it's a constant 5 pounds. So one way to do this would be, try to write over top of that. One way to do this would be to just have your integral and then have 5 in it. Okay, I'll put this up. I'll write it up here. You could have integral and then 5 plus, like that. Okay, so that's the bucket. But they went ahead and did the work. 5 pounds, 20 feet, 100 foot-pounds. Okay, next we have the water. Now, if it wasn't leaking, we would just put 16 pounds times 20 feet, right? But it's leaking. So how could we write the pounds of water? Let's do it over here on the board. It is leaking at a constant rate. We're going to make that assumption. Starts with 16 pounds of water and it's empty when it reaches the top. We will assume a constant rate.
So 0 minus 16 over 28.
So there are two good ways that I've seen problems like this done. One is to do it like an ordered pair, like what you're talking about. 0 feet, we got 16 pounds of water. 20 feet, we've got 0. It's a linear situation. So now we can just do the slope there, right? Subtract the y's, subtract the x's. What is that, negative 0.8? It's losing 0.8 gallons per feet. So we would have to multiply that by feet. What's feet in this problem?
If you're losing 0.8 gallons per foot, you're gonna get like 2.5 feet per gallon of water.
No, we have 16 pounds. Oh, not gallons. I'm sorry, not gallons. You're right. Pounds. I'm sorry. Pounds per foot, right? So we need to multiply that by feet. What unit is feet here? What variable? Distance. What would we use? How about x? X is the feet, right? In other words, so how many pounds of feet do you have, or how many pounds of water do you have in any given position? So at 0, you've got, okay? But now we need that's just the slope, right? I mean, so we have to add on what we start with, which is
20.
no pounds,
16.
16. So would it be that? Or now another way, a lot of times it's just people think this through. How many pounds of water do we have? Well, we start with 16, and we're going to lose, and then that's where the slope comes in. We're going to lose 0.8 pounds every foot. So wouldn't that be a way? I mean, you could just think your way through it and write it, I think, just about as easily. So one way to do it is slope. The reason I like showing the slope example, because sometimes it's not given this way. Sometimes, like in the rope, they tell you it loses 0.08 pounds per foot. But in the water one, they just tell you, well, it starts with 16 pounds and ends with nothing. So that kind of makes you think of 2 points. So you do the slope. So to get the negative 0.8, you kind of had to do that slope calculation. So that is, now aren't those units pounds? I mean, I want to make sure y'all are okay with this. This is pounds, right? That's a pound you start with of water. And 0.8 is pounds per foot, and x is feet. So pounds per foot times feet, you get pounds. So this is pounds right here. Okay, so I got 5 pounds plus 16 minus 0.8x pounds. So that's all pounds so far in my interval. Okay? All right, they go through, they do it a little differently in getting that proportion. 20 minus x is the distance it's pulled up out of a total distance of 20 times the amount of pounds is 16. But it ends up being the same thing. Okay? And they check it, and they say, okay, at 0 you got 16 pounds, and at 20 feet you have no pounds. Okay? So there's the water. All right, next, well, they go ahead and calculate that part of it. Okay, they go ahead and calculate that piece of it, so I'll go ahead and skip ahead. Because I think I like doing it this way better anyway. All right, and then we've now got the rope. Well, the rope, it's the same kind of thing. We start out with a certain amount of weight of the rope, and we're going to lose 0.08 pounds every foot. So what do you think? What would the equation for the rope be? It wouldn't be 20, because 20 is feet. We want pounds.
So it'd be 20 times 0.08?
20 times 0.08. How much rope do we have when it's all the way out, right? Well, it'd be 20 feet times 0.08 pounds per foot. So 20 times 0.08 pounds per foot is 1.6. Oops. Again, they do it a little different. 1.6 pounds is how much rope we have in the beginning. But we're going to lose 0.08 pounds for every foot. that we pull it up, and x is the number of feet that we've pulled it up. So it's very much like the water. Now, that right there is all pounds. That's pounds of bucket, plus pounds of water, plus pounds of rope. Now, how do we get feet in there so we get foot pounds? dx. dx. Okay? So now again, think about this. In the spring problem, we had our force equation, which was pounds, and then the dx was feet, foot pounds. Here, we're pulling up a bucket and some water and a rope, so our integral is pounds and the dx is the feet. And we get foot pounds. And the integral goes from what to what? 0 to 20. Because remember, this is dx, x is feet, so we are going to pull this from 0 to 20. Okay, so they go through and they get the same equation that we will get. 1.6 pounds at the beginning, no pounds of rope at the end. So they get the same thing. So you guys, anybody type this in? 276? 276 foot-pounds for the total. Okay, so that is the rope and the bucket situation. Now, on the quiz, it might be easier than that. I might not have a leaky bucket, right? This might be the rope and the bucket. So if it's just a leaky bucket, you'd have 5 pounds plus 16 pounds. You'd have 21 pounds in the bucket, and that's it. It stays 21 pounds all the time. The only variable would be the rope. Okay, it's pretty easy. How much rope do you have at the beginning minus how much you're losing? I mean, it's not that hard of an equation to write out. Okay? All right, the last situation. Pumping water. Okay, now this, again, the attack here is a little different. We're still using the integral to add up work. But instead of add up little bits of distance, this little bit of distance, this little bit of distance, this little bit of distance, we're going to use the integral to add up different slabs of water that we're going to, or whatever the thing is. This is water in this case. Okay? So this would be like your gas station example. This is all underground, the tank. 4 feet above ground is the nozzle where it comes out. Okay? So the idea is this. If we imagine the force is the weight of the water. So what we're going to do is we're going to say how much work does it take, kind of like the lemon, you know, what's the volume of one slice, and then let's let the integral add up all the slices. What we're going to do is what's the work involved to move this one slice of water up to 4 feet above the tank. Now I realize that it's going to drop down and then come back up. Okay, but we'll ignore that part of it because those will cancel each other out. The gravity and the weight involved going down and then coming up to here, right? Because if I fill this tank up, water's going to come here and there's going to be an equilibrium and it's going to match, and I don't want to get into all that. And we don't need to. But, so the idea is that it would drop and then come up. That's no additional work is needed there. So the idea is this slab will take a certain amount of work to raise to here. Slabs down here will take more work. Slabs up here will take less work because they have to go less distance. They're going to weigh the same, but they're going to go less distance. Okay, now what shape is that slab? A circle and with a little bit of thickness, right? So a cylinder, right? So what we need again is foot pounds. We need to add up foot pounds. So we want our integral to add up foot pounds. Now the question here is how we get the foot pounds. Okay? The dy, notice here, is not how far we're moving it. You know, in the spring, in the rope and bucket, we move it a little bit, move it a little bit, move it a little bit. That would be the dx piece. That's not what we're doing here. Okay, we're taking the whole slab and we're saying how much work does it take to move it up. The dx, in this case, the dy is that little bit. So it's kind of like our horizontal strip work we did. Okay, so let's start thinking about this. Well, how much does that slab weigh? That's the first thing we need. How many pounds? That's where we're going to get pounds here. How many pounds? How much does that slab weigh? Well, this is where the density comes in. Okay? In this problem, you would have been told the density of water is 62. I think in this example they use 62.5. In your homework, there's a problem you use 62.4. Okay? 62.5 pounds per cubic foot. So you would be told that in the problem. Okay? So we're going to use that. That's how we're going to get pounds of water. So what do we need to calculate for the blue slab? The volume, the cubic feet. And what's the volume of a cylinder? What's the volume of a cylinder? What's the formula? Pi r squared h times the height. So in our integral, we're going to have 62.5. Now remember, that's pounds per cubic foot, right? That's pounds per cubic foot. We're going to take that times pi r squared h. So again, what you find in this problem is you're just building the units that you want to come out. So pi, what's r squared? 5 squared, right? 25. Now those units are going to be feet squared, right? 5 feet is the radius. So 5 squared, that's feet squared. Times the height. What's the height of that cylinder though? It's in feet, but what do we label it? dy. That's where the dy comes in. That's where the dx or the dy comes in this problem. Not like it did in the other ones where we had pounds and then we ended up with feet by tacking on the dx because we were moving it a little bit, moving it a little bit, moving it a little bit. Okay, that's not what this one's doing. So the dy ends up getting in there. So look what we got. We got feet cubed, cancel feet cubed. Right now we got pounds, right? We got pounds. So what do we need? What else do we need? We need feet. So we can get foot pounds, right? We already got the dy, so we don't have to worry about that. So the question now is how far are we going to move this slab? I'll give you a hint. It's a lot like we've done with our strips and P in the shell method. It's a lot like we did with P in the shell method. Okay, I heard 10 minus y and I heard 14 minus y. How many vote for 14 minus y? How many vote for 10 minus 1? Oh, maybe I didn't hear 10 minus 1. 14 minus y. Because think about this. Here is, we're going to call this 0 down here. So the strip or the slab is at some y value, just like P was. So it might be down here at 2 or 3 or 4 or 5 or 10 or whatever. How far are we moving it? Up to here, 14, right? So how far, in other words, how far is the slab away from where we want it to end up? Same thing we did with P. Well, it'd be top minus bottom. It'd be 14 minus y. If it was up here at 10, it would be 4 feet away. If it's down here at 0, it'd be 14 feet away, right? 14 minus y is exactly right. So that's what we put right there. That is going to be feet. So we get foot pounds. We've got everything we need. Volume of the slab, or excuse me, the weight of the slab, which is volume times its density. We got the weight of the slab times how many feet it's going to move, foot pounds. Now, and I'll bet you get this one. The integral goes from what to what? Think about it a second, don't say it. The integral goes from, okay, go ahead. 0 to 10, not 0 to 14, right? The strip fills the space. Where's the water? The water's in here. The slabs go from 0 to 10. 0 to 10. Now, what if we were only going to pump this water up to the top of the tank and out? What would change in here? If we were only going to pump it up to the top of the tank. 10 minus y instead of 14 minus y, right? But it would still be 0 to 10 because the slabs are in here. What if the tank was only half full? The integral would just go 0 to 5. Still be 14 minus y, right, in this problem. But if the tank was half full, the strips, the slabs would only be from 0 to 5. So a lot of similarities to the stuff we've already done. Okay, so go ahead and type that in, see what you get. 441,786. Probably rounded that a little bit. All right. Now, we won't work through this next one, but we're going to talk about it just very quickly. Oh, and then they say if you had a 1 horsepower pump that was rated at 550 foot-pounds per second, it could empty the tank in just under 14 minutes. Okay. So we won't work through this one, we'll just talk about what's different. We've got a conical shaped tank filled to within 2 feet of the top with salad oil. A 10-foot tall tank filled with salad oil. All right. The salad oil weighs 57 pounds per cubic foot. Filled to within 2 feet of the top. How much work is required to pump oil to the rim? Okay, now let's talk about our setup here. What would change? Integral would be 0 to 8, right? Because the oil is only from 0 to 8. This would be 57. Okay? Now, one slab. Okay, there'd be one slab, one cylinder-shaped slab. So it would still be a cylinder, so it's still pi r squared h. So we could still have pi. What about the radius? It changes, right? In the last problem, our slab was the same size all the way through. Here, the slab changes. So its radius changes. But I think you'll be surprised at how similar, maybe not surprised, how similar it is to what we have done. How would you get the radius of that slab? What if you drew an axis right down here? The radius would just be the length of half the length of that strip, right? So all we would need is this x-coordinate. If we put the y-axis right here, we just need this x-coordinate minus 0. How can we get that x-coordinate? If we put a y-axis right here and an x-axis right here, we just need the equation of that line, right? And we know these values because we know it's 5 over to here, we know it's 10 up. So if we put an x and a y-axis here, we'd come over 5 and up 10. What's that slope? 2. And if our x and y-axis right here, if it went through the origin, what would be the equation of that line? Y equals 2x, right? So it wouldn't be that difficult to do. So we go ahead and we put that. Okay, they've got their density. Okay, they put the x and y-axis in there. There's the point. So that would be the line y equals 2x. So therefore this x-coordinate would be, this x-coordinate would be, this x-coordinate would be 1/2 y, right? 1/2 y. Just solve this for x. This x-coordinate would be 1/2 y. Okay? So that x-coordinate would be 1/2 y. So the radius of that slab is this distance right here, 1/2 y minus 0. So over here in our equation, pi times 1/2 y squared times dy. The only difference is the slab is not the same. Each of the slabs are not the same. The radius changes, but it's still a strip that we can do. Okay, so we get that. And then the dy, so there's our pounds. So all of this would be pounds, right? Density times volume. And then we would get our distance. And what's our distance? How far is that slab going to move? This is y right here. We want it to move up to here. How far is that? 10 minus y, right? 10 minus y. So 10 minus y is our distance. Okay, and you already said the integral will go from 0 to 8. So very, very similar situation. A little more difficulty because the slice is a changing amount. They go through all the rigmarole here, but that brings back memory. All right, 30,561 foot-pounds. All right, very good. So you're not going to have one of all of those on the quiz. I'll pick one. I'm not going to tell you which one, or maybe two. Okay, there's a spring, simplest probably one of all. There's the bucket and the rope, and then there's the pumping liquid. Okay, I think you have some of, one of each of those, I think, in your homework here, I hope. Um, yes. Okay, so the next line here, the next line on your thing in the book, 7.3. Got 5 problems, looks like, probably, that's like yesterday, probably finished those up in class, that's fine. Tomorrow is going to be packet work. If you're gonna be gone tomorrow, we're gonna do the, next multiple choice section on sample 4 and the first 3 free response questions. So there's 17, I believe, multiple choice questions. And the next 3, and the first 3 free response. And I will leave that information with the sub tomorrow, but if you're gonna be gone, that's what we're doing tomorrow. Monday, we've got one more new thing to do, we'll review a little bit. Tuesday will be a kind of a review worksheet on some volumes and things like that. We'll talk about packets a little bit. Wednesday will be that quiz. We haven't had many grades for a while. They'll start coming fast and furious here.
I've had any grades since I lost my test.
Uh,